All right, today we're taking a look at radical equations. And as we've previously seen in chapter 9, radical equations are, the way that we solve them is essentially speaking the opposite of what we did when we were taking the square roots of equations. So previously we would have something like x squared equals 9. And in order to solve for x, we'd take the square root of both sides. And that would give us x squared, that would not give us x squared. It would give us x equals plus or minus 3. Because whenever we would take the square root, we would have to then consider the fact that when we square something, when we're squaring the x here, -3 squared is also +9. So what we're going to be doing is we're going to start with the radical and then go back and take the square root. And this idea here is related to things we've already seen before. For example, if we were to look at the square root of x is equal to 3, for example, in order to undo our square root, we would just square both sides. And when we square both sides, the square root of x squared is x, and 3 squared is 9. And if you think about what radicals mean as fractions, this might provide some additional explanation as to what exactly is going on. When we take x squared and we take the square root of it, this is actually the equivalent of saying taking x squared to the 1/2 power. And then applying the power rules, 1/2 times 2 is 1. And x to the first power is equal to the x that we end up with over here. Likewise, if we have the square root of x, that's the same as saying x to the 1/2 power. And as a consequence, if we were to square both of these, we would then multiply 1/2 by 2. 1/2 by 2, of course, equals 1. So that's sort of the exponential explanation as to why this works. Essentially speaking, what you do, though, is when you have a root, a radical like this, it's going to have some number that's sitting right here. I'm drawing an n in the case of a general one. When we have an n sitting right there, we take the radical to the n power. If there's no number listed there, that's a square root then, so you need to use 2. Otherwise, for example, you would have the cube root. To undo that, you take it to the 3rd power. If it's the 4th root, we take it to the 4th power. So it's pretty easy, and then you just need to apply what you've done to the other side. Now, taking things to the 4th power would be kind of annoying because those numbers can get big real fast, but we're not going to see anything too crazy in our example video today. So let's look at a few examples and see how we can solve these. Our first one is going to be the square root of x plus 5 is equal to 13. And solving one of these equations is not significantly different than solving any of the other equations we've worked with. In order to solve for x here, we need to isolate the square root of x by subtracting 5. Again, our classic opposite operation. That gives us the square root of x is equal to 13 minus 5, which is 8. And then in order to undo our square root, we need to square both sides. The square root of x squared, that's like our 1/2 times 2. That just gives us an x. And 8 squared is 64. And that's it. Notice that we only have one solution here. If we were going to have multiple solutions, we would either need to have an x squared term like we had up here, or alternately, this would have to say plus or minus the square root of x. Since it's just the square root of x, we get to assume it's plus. And as a consequence, most of these radical equations, at least the ones we're looking at in this video, will have just a single solution. For another example, that was our first example. For example 2, we're going to look at 3 minus the square root of x is equal to 0. And once again, we need to isolate the square root of x. And I'm going to start by subtracting 3 from both sides. That gives us negative square root of x is equal to -3. And you might be tempted to say, all right, well, all we got to do now is square it. And secretly, that would actually get us to the correct answer, although probably not for the reason that you're necessarily thinking. What I'm going to do is I'm going to get rid of the negative sign because I just want to have a nice, clean square root of x sitting there. So I'm going to divide the negative sign away. The negative sign, of course, is a -1. We don't include the -1 because, we're mathematicians and have to make things hard on everyone, and because we're lazy and don't want to have to write -1 over and over and over again. But in order to divide away the minus sign, we divide by -1. The negative square root of x divided by -1 just gives us the square root of x, and -3 divided by -1 is +3. Finally, we square both sides, and we end up with x equals 9, as once again, 3 squared is 3 times 3, 3 multiplied by itself 2 times. And hopefully by this point, you're saying, wow, these problems are pretty straightforward. We're going to look at a couple more complicated ones here, but ultimately, I think you'll find that none of the ones we're doing in this video are overly complicated. You just need to know when and how to square things, and you should be good. We'll look at some cube roots and maybe even something a little bit crazy in one of the later videos for this section though. But for this example, this one's going to require several algebra steps to solve. We have 4 times the square root of x plus 2. Outside of our square root, we have a plus 3, and then we have the whole thing equals 19. So in much the same way that many of our problems have proceeded in the past, we first need to get the thing that has our x trapped in it alone. So we need to get this square root of x plus 2 all on its own before we can square it in order to drill down and get to the x. So to that end, I'm first going to get rid of this 3 here, because before I can divide by the 4, I have to subtract the 3, otherwise I have to divide a bunch of other extra junk by that 4. So I'm going to subtract 3 from both sides, and by doing that, that leaves us with 4 times x, the square root of x plus 2, is equal to 19 minus 3, which is 16. From here, before we square the square root, in order to make my life easy, I'm going to divide by the 4 on both sides. If I were to prematurely square something, that would result in me needing to square every single term, meaning I'd have to square 16 and 4, and that would just be annoying. It would just give us unnecessarily large numbers. So the easiest choice is to divide first. When we divide 4 by 4, it goes away because 4 divided by 4 is 1, and 1 times the square root of x plus 2 is the square root of x plus 2. 16 divided by 4 is also 4. Now, we can't access the plus 2 that's inside of our square root without getting rid of the square root first. So we need to take both sides to the second power by squaring now. Finally, we square the square root of x plus 2. Conveniently, that just gives us x plus 2. And 4 squared is 16. And in our final step, we would then subtract 2, yielding x equals 14. Now, if you're not sure if this is actually the case, we can go ahead and plug our x equals 14 back into our original equation, which I'll spend a moment doing. I have just replaced x with 14 in the original equation, so you can compare. The only difference is x is now 14. 14 plus 2 is 16. The square root of 16 is the number you multiply by itself in order to make 16. That number is 4, because 4 times 4 is 16. This gives us 4 times 4 plus 3 equals 19, which is to say 16 plus 3 equals 19. So it does in fact check out. And this is something you can do. You can always go back and check your work manually by plugging your solution back into the original equation. And that is something we're going to have to do in our second video, because not all of our solutions are actual solutions, which we'll see later. But for the moment, we're focusing on just the comparatively straightforward examples. We have one more example here today. And this one, starting to get a little bit crazy, although you'll find it's actually a little bit easier than you might think. And this one is the square root of x minus 1 equals the square root of x plus 4. And we have 2 x values running around in this one, but the issue is that they're in 2 different square roots. So we can't do any like combining like terms. We can't basically do any operations at all right now until we get rid of those square roots. But the thing that's convenient is, since both sides of the equal sign are entirely contained in our square roots, we just get to square both sides and the square roots will go away. So if we square each side here, we just get 2x minus 1 equals x plus 4. And from here, it's just a few steps. I'm going to subtract x from both sides in order to get all of my x's together. 2x minus x is just x. That's like 2 minus 1 is 1. And 1x, of course, equals x. And then we have still the minus 1 on the left side. That was sitting right there. And our plus 4. We add that 1 to both sides, and we get x is equal to 5. And if you really wanted to, you could quickly check. 2 times 5 is 10. Minus 1 is 9. The square root of 9 is 3. And then 5 plus 4 is 9. The square root of 9 is also 3. So those are 4 different examples of solving using square roots. And you need to be careful in these examples to figure out when the best time is to square that square root we have running around. So in number 4, for example, we couldn't do anything until we squared it because there was no way we could combine those radicals together. In 3, we isolated the square root of x plus 2 and then finally squared at the end. In theory, you could have squared just about anywhere, but it would have made the problem a lot more annoying to do depending on when you do it. And generally, you want to try and save your square rooting until closer to the end. And our first 2 problems, we actually were able to solve them directly after taking our square. So it made sense to isolate simply the square root of x and then square it to find our answers. That's a quick rundown on solving radical equations. It pretty much just requires you either square or cube or basically just take the equation to whatever power is being used to take the root. So if the root is the square root, we would take it then to the second power. In our next video, we'll see an example where instead we're taking the cube root of something as well as identifying some extraneous solutions. Actually, I take that back. We're doing the cube roots in the third video. We'll be identifying extraneous solutions in our next video, though.